Here we come to 2.5, which I think is the most important section of this whole chapter. In the beginning of it, we had a little thing about being able to do synthetic division, right, to prove things are zeros, a little bit about graphing and end behavior. It's with this section right here that we're going to get the tool set to, no matter what polynomial we're given, find the zeros of it, which will kind of complete that 2.2 section where we did end behavior, we knew if it bounced or crossed, but it was sometimes a pain to find the zeros unless we were given a heads up. This section is going to let us find them all from scratch. So part of that comes first from the fundamental theorem of algebra, which is at the top of your page. And more or less what this is saying, if we're dealing with a polynomial of degree n, and it's a positive degree, then it's going to have at least one zero in our complex numbers. Now, the important thing about this is it means that when we're searching for zeros, we're going to find them. So instead of pointlessly kind of working through these and ending up with none, like we would have in the past, right? So maybe we would have done something with quadratics, done quadratic formula, had a negative inside, said, oh, no zeros, can't do anything. Now that we have complex numbers, we can include that, so no matter what, we'll get some type of information from that function. So first, we're just going to do a little bit of practice of finding zeros before we learn how to kind of hunt them down in the first place. So for number one, real straightforward, right? It's just a linear polynomial, linear function. We have x minus 4 equals 0. You solve for x, you get x equals 4. Not too bad. Moving on to number two, typical quadratic function. We have x squared minus 4x plus 4 equals 0. I suppose worst case, we could take this and plug it in the quadratic formula, but this one's not too bad. This is just x minus 2 squared, right? Negative 2 times negative 2, we get the 4. Negative 2 times x, then double it, we get the middle term. So that's just x. Minus 2 squared, so reminder, multiplicity of 2. If we were graphing this, it would bounce at that point, which makes sense for parabola. Solve for the 0, take the square root, move the 2 over, we get x equals 2. Now moving on to things like 3 and 4, a little reminder of some tricks. For the first, we'll get it written out. Setting this equal to 0 to find the zeros. These both have an x in common, so we can pull that out. We can factor it out. Well, we can go a little bit further, right? We could take this if we wanted to, and we could set it equal to 0 and solve. Sometimes it's a bit of a pain to remember, though, right? We'll have to take a square root, do the plus and minus, right? Positive and negative of that root. But this is also something else. See if you recognize it. We got a difference of squares. So this is nicely factorable as x plus 3, x minus 3. I personally find it easier to kind of eyeball, oh, look, difference of squares, and get that written down, rather than relying on remembering to do the plus and minus for your root. You set all these equal to 0. We're going to get x is 0, multiplicity 1. X is negative 3, multiplicity 1. And x is 3, also multiplicity 1, which tells me on all three of these zeros, with all odd multiplicities, we're going to cross through each time. Now we bring up to number 4 something quartic. So we have x to the 4th. So we get it started. This is equal to 0. And it should look semi-familiar to what we just did over here on number 3. Over here we had a difference of squares. We have that same thing happening over here. This is really x squared squared minus 16. So you could more easily see that difference of squares. Well, then that gives us two things. We have x squared plus 4 and x squared minus 4 equals 0. We got one more in there, right? X squared minus 4 is another difference of squares. This one's close, but because it has that addition, we can't do anything with it yet. So we have x squared plus 4, now x plus 2, x minus 2. And last, we could set each of these, set equal to 0, solve. This one is the one that really catches my eye, though, that I'm going to work out. Got 4, we subtract it over, so we have x squared equals -4. I'm going to take the square root on both sides and get x is equal to plus and minus square root of -4. But we don't do -4 anymore, right? We rely on our complex numbers. We would take that out. So from here, we would have square root of 4i. And then we know square root of 4. Oh, let's not lose our plus and minus. Square root of 4 is just 2, so this is really plus 2i and minus 2i. So plus and minus 2i. So lastly, for all of our zeros, we have x is -2, x is 2, x is -2i, and x is 2i. Here at the bottom of page 1, we have kind of the bread and butter for this entire section. And it's called the rational zero test or rational root test. And ultimately what it says, and yours is in a slightly different form, if we have some polynomial, and for mine I made a little tiny change on the board where the leading coefficient is q, and that constant term at the very end I'm calling p just for a little consistency. If you have some polynomial, then every single rational zero, so something that's a fraction, any rational zero that exists for that has to be in the form of either the positive or negative of some factor of p over some factor of q. Now, the big reason this is important is because it takes this endless list, right, and it really thins it out to simply be a few values for you to test to find those zeros. As we did in our earlier sections, 2.3, right? If I gave you a 0, then we can use synthetic division to kind of help us factor those bigger polynomials. And that's exactly what we're going to do. That's our main point of 2.5. Step 1 is always going to be to list all the possible rational zeros. And we'll see some of these lists can get kind of tedious, kind of long. After you list them, you need to test each zero. And there's 2 ways to do this. Today, I'm going to be using the graphing calc to help out, because if I have possible zeros and I plug that 0 back into the function, what do I get? 0, right? So if I have a list of possible zeros and I start plugging them in to see which one gives me 0, once I find it, then I can use our synthetic division with that known 0 to take something, say, that's cubic that I can't really factor into something quadratic in which I could either factor or do quadratic formula for. So we're going to be making lists, testing them. We're going to find those important zeros. We'll use synthetic division. That'll help us whittle down that problem. And the end goal is that we're able to find all the zeros of the polynomial now from scratch, rather than someone saying, hey, guess what? 7 is one of our zeros. So to kind of see what this list looks like, if you move on to that second page, got the top few problems. We'll start with number 5. So the big thing to identify first is what is p, the constant term, and what is q, the leading coefficient. Well, for us, p is -125. We could almost just say 125 because we got to look at the positives and the negatives. And q for us is right here. It's just a 1. So here's what's really nice when our leading coefficient is a 1. If it's the factors of the constant term over the factors of the leading coefficient, and that's a 1, well, anything divided by 1 is just itself. So instead of having to even bother with the factors here, we're really just looking at the tail end over here. Because a factor of 125 is, say, 1, but 1 over 1 is 1. A factor of 125 is 5, but 5 over 1 is 5. So as long as our leading coefficient is 1, it saves us a ton of trouble. So number 5, I'm going to list the possible zeros. That's step 1. So here are my possible zeros. Factors of 125, we have plus and minus 1, again, over 1, if we wanted to, but that's just going to give us 1, so I'll keep it simple. We have plus and minus 5, We have the positive and negative 25, that's a factor. And then lastly, we have positive and negative 125. So again, we got that from our constant terms divided by the leading coefficient. So technically all these, right, would be divided by 1, but that would just give us the same thing. So if we have a rational zero, it has to be one of these. Now, we can test it with synthetic division. We could do guess and check and do synthetic division over and over and over and over and over until we get a remainder of 0. But we have calculators for a reason, right? We can speed up that process. So on your calculator, you can input your function with the y equals, go to second table, and we can just test these values until we find one that works. Then we'll do synthetic division. So I'm going to test it. Sadly, f of 1 gave me negative 64. That's not helpful. F of negative 1, that gave me negative 216. So that's like a remainder if we did synthetic, right? Not helpful. Next is 5. F of 5 gave me a 0, which is important because now I know at least one of the zeros has to be a 5. So now we can dive into our synthetic division. So we'll get our synthetic division going. We know one of the zeros is a 5. Again, we'll pull our coefficients from our original, 1x cubed, negative 15x squared, 75x, and negative 125 for the constant. And we're just going to do synthetic division. In fact, we already know the remainder has to be 0 because we just found out it is 1 for 5. So we'll bring down the 1, 5 times 1, 5, add it, negative 10. We'll get negative 50, add it, we get 25, we would get 125. Now here's what's nice, right? We started from nothing, made this list, checked it twice, tested it, right? We found one that works, so we have at least 1 0. I now boiled it down to this. Now I can do one of two things here. I can keep testing all these possible zeros, and I'd start from the very beginning again. So I'd start at 1 and test all those again on this new one. Or, that's really nice, right? This is just x squared minus 10x plus 25, which is something we really like. That's super nice and factorable. That's just x minus 5 squared. And again, we can get our zeros straight from that. We have x equal to 5. And then this is x equals to 5, not once, but twice, right? So then x equals 5 with multiplicity 1, 2, 3. So for this polynomial, this cubic, that little S shape, it's only going to cross the x-axis once at x equals 5. And I'll make note that has multiplicity equal to 3. So we're on, say, 2.2, 2.3. We were given zeros. Now with a little help of our rational root test and either a calculator and some synthetic, we can start from scratch and find exactly where our zeros are, which we're going to keep doing for the next two. So moving on to number 6. Number 6, our P is 4. Our Q again is 1, which makes it really nice, right? So our possible zeros, we're going to have 4 over 1, although I typically like to start with the factor of 1. They always share that. Another factor of 4 is 2, so plus or minus 2 over 1, which is 2. And then plus or minus 4 over 1, which is 4. Now again, you could test each by hand on synthetic, so if you didn't have a graphing calculator, this works just the same. But I got one, hopefully you do too, kind of speed it up. So looking at this, we're just going to plug it in again to our y equals, and we're going to go in here and we're going to test all of our points. So we have f of 1, this is 5, then we have f of negative 1, which is negative 9, Now we have f of 2. That's 24. Oh, not looking so good, right? But we still have time. F of negative 2 is negative 16. Some of you may have already caught on based on how much room I gave this one. F of 4 is a 1/16. And f of negative 4 is negative 60. So here's the interesting about this one. Where we found a rational zero that worked out, this one actually doesn't have a rational zero. If it didn't show up from one of our possible, this tells us this has no rational zero. And this will be the only time where we're not able to kind of work more with those polynomials. So as we see here with this one, we have no rational zeros that showed up, which means the zero has to be irrational. And this is one of the rare cases with this tool set where we run into kind of that does not exist kind of finality of it, where using this test sadly still didn't give us enough information, in which case this one's still kind of out of our reach for being able to deal with finding those zeros. So that is fair game. And now for number 7, I'm not going to work the entire thing out and find the zeros, etc. But I want to go about it 2 ways for finding my possible zeros. For one, we have P, which is 4/9, Q, which is 1. And now the factors of 4/9 are plus or minus 1/1, plus or minus 2/1, plus or minus 4/1. And then we got to do it again, plus or minus 1/1, plus or minus 1/3, the factor of 9, plus or minus 1/9. And it can kind of get confusing of what you need to do if we're stuck with a fraction. But alas, we have a nifty little trick for us. I'm going to rewrite this polynomial. So we get x cubed minus 1/9 x squared minus 4x plus 4/9. And I'm going to set this equal to 0. For the reason is we'd be trying to find zeros, right? Now there's something we've done before, kind of rarely, but I've said it a couple of times of, I don't like fraction. So anytime I see fractions, I always take advantage of being able to clear the denominator. So that's exactly what I'm going to do. Given this, although it'll change my leading coefficient, it's going to make it a little easier to see those factors. So if 9 is this denominator I need to clear out, then I'm just going to multiply everything by 9. So here I'm going to get 9x cubed. 9s will cancel here, so minus x squared. We'll get negative 36x. And then lastly, it'll cancel at the end, so we'll get plus 4. And that's still going to equal 0, which means clearing that denominator out didn't actually change what my zeros are going to be. However, it does make it a lot easier to see my new factors, right? Where P is going to be 4, Q is going to be 9. So now I'm looking at the factors of 4 over the factors of 9, which is a little more simple to view rather than remembering to break the factors of this one up by itself. So if that's the case, factors of 4, 1, 2, and 4. Factors of 9, 1, 3, 9. And we need all of those combinations to come together. So we get plus or minus 1/1, which is 1. Plus or minus 2/1, which is 2. Plus or minus 4/1, which is 4. Now we get the weird mixes in. Well, plus or minus 1, we kind of start back at the beginning, over 3. So plus or minus 1/3. Plus or minus 2/3. And then plus or minus 4/3. And almost done, but a couple more, because now we need to do it one more time with everything over 9. So keep going, we plus or minus 1/9, plus or minus 2/9, and plus or minus 4/9. Now, hefty list, but I think a little easier to see if I clear that denominator, it makes it nicer to see specifically what is P, what is Q, and what their factors are. And then one last thing we'll see in some examples coming up is if we have a repeat, so say for example, I had a 3/9 over here, but I already have 1/3, we don't need to list that repeat. So that's a nice thing about finding these possible ones. Now again, this one we're not going to solve out, but I just want to show if we have to, we can clear those denominators. Does throw something in Q for us, so now we have something in the denominator when we look at factors, but a little more straightforward. But now we're going to do a couple more problems where we start with a leading coefficient other than 1 in the first place. As we get to the bottom of that second page, and as we'll see on number 9 on the next page, we now have leading coefficients that aren't 1, which means when we look at possible roots, we're not just looking at the constant term over 1, or aka the factors of just that. We got to look at the factors of that over now the factors of 4. So if we're looking at factors of 3, it's 1 and 3. Factors of 4, 1, 2, and 4. So let's look at our possible factors. We'll make that list. Oh, we have 1 over 1, so plus or minus 1. 3 over 1, plus or minus 3. 1 over 2, plus or minus 1/2. 3 over 2, plus or minus 3/2. And then we have 1 over 4, and then 3 over 4. Plus or minus 1 over 4, and plus or minus 3 over 4. Now again, if we had a repeat, say this was a 3 out front, we had 3 over 3, we would already have that with that plus or minus 1, so we don't got a repeat. Now, we could do one of two things. We can do synthetic division and test all of these by hand, totally fair, or once again, we can rely on our calculators to let us know which of these are zeros so that we can start with our factoring. So if we take our calculator, we plug in our function, and then I'm going to go to second graph, which gives us our table, and we're just going to be testing these to find out if any of them work. So positive 1, f of 1 gives me 10, that doesn't help. Negative 1, f of negative 1 already. I have a 0. So I can now use synthetic division to factor this guy out. So get our synthetic going. We know that negative 1 is going to be one of our zeros. We've got 4, 8, 1, negative 3. Bring down the 4, negative 4. Do it again, we get negative 4. We should be getting negative 3, 3. And as to be expected, we get 0. Now we can do one of two things at this point. We can take this, that's 4x squared plus 4x minus 3. We could factor that, that's not horrible, or worst case scenario, we could do quadratic formula. But if you didn't want to go down that route, we can, well, I guess I'll keep it up for a second. We could take this polynomial now and run through the list of possible zeros onto this. So if you wanted to, you can enter this function into your calculator, hit second table, and then we'd be testing these same possible roots, right? Because we have those same factors here, the negative 3 and the 4, same as above, on this new polynomial to see, is there something that is another rational root? So we'll run through this again. 1, no, 2, no, negative 1, negative 2, sorry, not 2, 3. We got 1/2, and just right there, I see that 1/2 works. So again, we could have factored this like we did in 2.3. We probably would have taken this and factored it. But since we have a list of possible zeros, we might as well try them out. It's a little bit faster than going through, say, all that quadratic formula. So I just ran that new polynomial, and I ran through our possibilities and saw that f of 1/2 also gave me a 0. So we just do synthetic again, right? Bring down the 4, half of that is 2, 6, half of that is 3, as we expect a 0. Now, instead of having to even do quadratic formula or do some messy factoring, we're left over with this, 4x plus 6, or if we wanted to, 4x plus 6 equals 0. Subtract the 6 over. So we have 4x equals negative 6. Divide by 4. We have x is negative 6/4, which is not quite what we want. We want to simplify that, right, as negative 3/2. And this is rational. And to be expected, it's in our possible list. So again, at the second point, you could have gone quadratic formula like we did 2.3, but I want to keep using this skill set because it cleans it up so much easier than having to deal with quadratic or factoring, leaving me with x equal to negative 1, 1/2, and then negative 3/2 as my zeros for this polynomial. So again, list your possibilities. You can test them when synthetic, which as we see, it's not too bad when you get used to it. Graphing Calc is going to help speed it up a ton though. And then from there, when we find a possible one and we bring it down to something we know how to use, so for example, something cubic to something quadratic, we have a bunch of tools for quadratic, or we can just continue with this new one, and both of them will get us to this final answer. So as we move on to the next page, we have number 9, which is pretty much the same thing. The difference is it's asking us to solve this polynomial equation. So it's already gone to that next step of finding zeros for us. So exact same setup. Give number 9 a shot yourself. Give it a pause. When we come back, we'll see it kind of worked out, and we'll kind of walk through that process again to see how we're able to take advantage of this rational root test. Hopefully you gave it a pause and you gave it a try for number 9. I already have it worked out here for us. I'm just going to kind of walk us through it one more time. So if we're looking at possible roots, it is our p, positive 18, over the factors of q, which is our 2. So we get plus or minus 1, plus or minus 2, so all the factors of 18 over 1. We then get all the factors of 18 over 2, but we have some repeats in here. So like the last one I have here is plus or minus 9/2. If we were to continue, right, we'd say plus or minus 18/2, but we already have 18/2. That's right here. So that's what I mean by when we have these repeats and it's already on our list, we don't actually need to include them. Now, this is a lengthy list, right? Quite a few possible zeros, which is why, although synthetic works to check them, I really suggest that Graphing Calc. The first one I found was -1 as a 0. So then I did synthetic to get this new little bit to hopefully be able to either factor, which looking at it was kind of not really feeling it on the factoring. I went through and tested the rest of my possible roots, and sadly, none of them gave me a 0 on this. So I went to, well, what do we know to solve quadratic? We know quadratic formula. So we had our negative b, so positive 3, and then we had it plus or minus the normal jam, right? The big emphasis I want to put is, as we talked about it in earlier stuff, 2.4 especially, this came with the positive and negative, right? So we have those conjugates happening of zeros. So we always know quadratic formula is going to spit out 2 different answers, 2 conjugates for us. So if we get one, we can already assume the other. So we end up with the roots of -1, and then 3 plus and minus 3 root 17 over -4. And you could have changed the form a little bit. You could have moved the negative from the bottom to the top. But big point being is when we have these possible roots, if even one of them works, which it did, it brings it from something that we have no idea how to deal with to solve down to something we've done for actually a couple of years now. But as we typically go from one direction, polynomials and finding our roots, we're going to work in that other direction. We're going to have some roots and try to create the polynomials that come from it. So as we come to the bottom of that third page, we have 2 different problems. And some of you might notice, hey, Hoffman goes from 10 to 12. Yeah, there's a typo. There's no number 11. That's fine, though. But in these 2 problems, I really emphasize something. There's a very slight difference. They almost look like just the same thing on repeat. But for number 10, we're asked to find a 4th degree polynomial given a couple zeros. And for number 12, we're asked to find the specific quartic polynomial, given these zeros and a little something extra. So we're going to kind of see the difference of these two as we produce polynomials given some zeros. Well, for starters, we're asked to find a fourth degree polynomial, which means we should have technically how many possible zeros? Not quite 3, but 4, right? So unless there's a repeat in here that we're not told about, there needs to be a fourth 0. So take a second and see if you see that fourth 0 already. We just kind of talked about it from the last problem. We didn't have normal conjugates, we now have complex conjugates. If I'm told negative 7i is one of my zeros, then that means positive 7i, its complex conjugate, has to also be one of our 4 zeros. Well, if we know the zeros, then we can write the factors. So we have f of x is x. For here, we're going to say minus 2, x plus 2, x plus 7i, and x minus 7i. Now there's one little detail, let me kind of match it with the color. If I'm finding a fourth degree polynomial, I don't know its kind of vertical stretch or shrink that's ultimately happening outside. And so we need to leave that as just, well, an a. We don't know what that constant is yet because we're not given enough information for this one, but it's just going to be part of our general form. So it's going to kind of trail down with us. So now at this point, we're just kind of dealing with a lot of FOILing, right? But the nice thing is for these first two, x plus 2, x minus 2, that should sound familiar. That should sound like a difference of squares, x squared minus 4. And then we kind of have something similar. If we remember dealing with multiplying conjugates by one another, we end up squaring the first. The middle term would drop, right? Negative 7xi, positive 7xi, that cancels. And then it's 7i times negative 7i. So we get negative 49i squared. But remember, when we get that I squared, it just changes the sign. So, or if you remember the little trick where you square the first and add it to the second squared, we can skip quite a few steps on that from having to actually hand FOIL all this stuff out. However, for this last little bit, we do need to. We got a little bit more we got to do. Again, this a is staying with us. It's not going anywhere because this is a possible polynomial. So we FOIL, we get x to the fourth. We get plus 49x squared minus 4x squared, and we have 4 times 49, so minus 196. And again, this is all in parentheses. Now we got a tiny bit more, got some like terms in the middle. And I'm going to keep this a in red. We get x to the fourth plus 45x squared minus 196. And we have this a out front that we don't have enough information to solve for. So we did this before when we did quadratic. So we found a quadratic polynomial for us in the past. But we had more specific ones when we were able to throw a point at you that you know it goes through and then solve for that vertical stretch or shrink. Now, however, this just asks for a fourth degree polynomial, so we are indeed done. And whenever we produce a polynomial that is only changed by that stretch, right? Because all the zeros, no matter what we put for a, all the zeros have to be the same. We ultimately create what's called a family of functions. As this polynomial will produce relatively that same shape, it's just some things are going to be steeper and some will be a little more smashed out, but still going through those same 4 zeros. Now, very, very similar process over here on number 12. So I'm going to have you guys give it a shot on number 12, just getting to here, and then we'll kind of reconnect and find out how do we use this last little bit to find the specific quartic polynomial given those zeros. So again, use part 10 or number 10 as a model. You guys are going to get down to this point, and then we'll connect from there. Hopefully you gave it a pause, Worked out that first part, very similar to number 10. In fact, same thing, just different zeros. A big thing to remember here is, again, complex conjugates. If I have one zero that's complex, I can produce one more. If we have 2i that's given to us as a zero, we need its complex conjugate, so negative 2i ends up being that fourth zero for us. So if we know the zeros, we can write it as the factors. Again, we have an a because so far we're just producing a polynomial. So you work your way down, little foiling, simplify everything out. So now I know that f of x is equal to this a times x to the fourth plus x cubed plus 2x squared plus 4x minus 8. But this was just a polynomial. Now we need to use what we're given. We know that f of negative 1 is 10. Well, if we have f of negative 1 right here, we know this has to equal 10. We don't know what a is. And then for every single one of these x's, we're going to replace it with negative 1. So we have negative 1 to the fourth plus negative 1 cubed plus 2 times negative 1 plus 4 times negative 1 minus 8. And again, we keep that a. We're solving for that is really our goal. So from here, we get positive 1, negative 1, negative 2, negative 4, minus 8. And then when we simplify all this, this is a positive 2. That should have been squared. When we simplify all this, we're going to get 10 is equal to a times negative 10, which ultimately tells me that a is negative 1. Now I know it's so easy to stop right there. We found it, we're done, right? There's the quartic, we're good. But we need to kind of rewrite it now from right here with knowing what a is. And in fact, I'm also going to distribute a at the same time, which really means we're just multiplying negative 1 times all of these. So we have the polynomial as negative 1 times x to the fourth, so negative x to the fourth, minus x cubed, minus 2x squared, minus 4x plus 8. Now this will be the specific quartic polynomial that goes through these zeros, but also specifically through this point. So there's the big difference between creating a possible versus the specific polynomial. And now we're going to kind of combine all this stuff together on our last page. As we come to this last page, we're going to be taking all of our knowledge so far, whether it's from complex numbers, quadratic formula and factoring, synthetic division to help factor, rational root test, whole bunch of stuff, right? And now we can approach all these polynomials to find all of their zeros. Well, as we start with number 13, they were nice, and they already gave us a zero of 4i. So right off the bat, if I know a zero, I might as well dive right into doing synthetic division. So we got 3, negative 2, 48, negative 32. Make sure you didn't have any zero placeholders. We're good. I should already expect this should be a zero, right? Because I know this is a zero. So we'll just do synthetic. 3 comes down. We get 12i. Negative 2 plus 12i, so negative 2 plus 12i. We'll multiply, we get negative 8i. I'll kind of put that at the end. And 4 times 12 is 48, but we're going to get the I squared right there, right? And I squared gives us that negative 1, so whenever we have that, it just is a sign change. So negative 48. Well, that's really nice for us. If we're adding down, the 48s cancel, and we're left with just negative 8i. And if need be, if you have that little bit of OCD and you got that 4 times negative 8 is negative 32, the I squared is positive 32, as we expect, it's 0. Now, we could write this as a quadratic and try to factor it, I guess. But we already know another 0. We don't even need to do the rational root test, right? We already know another 0 because the 0 they gave us is complex. So if 4i is a 0, so it's its conjugate of negative 4i. So we can do that here. We have the 3 coming down. We get negative 12i. That's extremely nice, right? Now the 12i's cancel. We just get negative 2. And here we're going to get positive 8i. As we expect, it should be a 0. Now I'm dealing with something that I want to factor or deal with solving. So I got 3x minus 2 equals 0. Add the 2, divide by 3. I get my third 0 of 2/3. And then I also have my positive and negative 4i. So when they give us a 0, even though it has the I, and we got to do a little of that arithmetic, right? It's not that bad, and a bunch of stuff cancels. Far nicer than looking at these two factors, which we could have done of x plus 4i, x minus 4i, FOIL them, then do long division instead. Bunch of headaches. We can avoid that every time. We can do synthetic, get it down to something we can work with. So as we look at number 14, it's almost identical, right? They give us a complex 0, which means its conjugate is also going to be one of our zeros. So take that into consideration, give it a pause, and give number 14 a try. Very similar to number 13, right? So I hope you gave it a run through. So number 14, we first have 1 plus 4i is a 0, and we kind of work our way down, right? And as we do synthetic, this second step is the one that really gets us. So for any reason we ever have two complex numbers multiplied, we ultimately have to FOIL, right? It can get a little messy. Never hesitate to kind of work that off to the side. So if you needed to, plus 4i, if you needed to work that off to the side, then see what you get. By all means, do it. It keeps it cleaner in your synthetic, and then you can practice that outside of it. Well, for the first, we end up getting remainder of 0. We know this because it is 1. Complex conjugate comes with it. So we get 1 minus 4i. We do the same thing. The nice things on that second one, the 4i's cancel. And then finally from here to interpret it, this first one has to always be the constant term. And then we build x, then x squared, etc. So this is just x minus 2. Set that equal to 0. We get 2. So we get our 3 zeros as 2 and 1 plus 4i, 1 minus 4i. So 1 plus or minus 4i. So even if the 0 they give you is complex, and I know we had some homeworks where we had square roots over here, and we kind of ran into that very similar thing as we should. I is just a square root of negative 1. It isn't as bad as, say, FOILing everything and doing long division. So now we move on to number 15. Number 15 has no zeros given to us. However, it's not too bad, right? Our leading coefficient, our Q out front is a 1, and our P is a 9. So if we look at all of our possible roots, well, for our possible, we're going to have the factors of 9 over 1. So plus or minus 1 over 1, which is just 1. Plus or minus 3 over 1, which is 3, and plus or minus 9 over 1, which is 9. Now, if this has a rational root, then we can test it again. You can get out your calculator. You could plug it in on the y equals, go second table, and I'm just going to start testing them from 1 and start growing from there. And right off the bat, f of 1 is 0. So we already have our first 0, nicely worked out for us. It's 1. Now, just a reminder, when we do synthetic on this one, it's a quartic, but it's really short. So we need to remember to put the placeholder of 0 in for the cube term that's missing, and also a 0 for just the x term that's missing. And I'm putting the 0 there because I'm expecting it, because this, well, it is a 0. So the 1 comes down, 1 times 1, we get 1, do it again, 1, we get 9, 9, 9, and boom, we get 0. So now we have this new thing right here. If we wanted to, this is x cubed plus x squared plus 9x plus 9. It's not the friendliest polynomial yet, right? So why don't we continue to see and just double check, hey, if there's one more rational root in here, then that might save us some trouble. So to go through, I'm going to try more of these, and again, right off the bat, f of -1 gives me another 0. So I can run through this one more time. But now I'll do it with -1. So the 1 comes down, we get 1, -1, 0, 0, 9. As I expect, -9, and then 0. Now this might be something a little more usable. So I see that this is a 9 for the constant term, 0x's, and then 1x squared. And here's why I know none of my possible are going to work anymore. If I set this equal to 0, what happens? Let me make it look like a 0. If I set it equal to 0 and I subtract the 9 over and take a square root, we're now in the world of complex zeros. So I know it can't be something rational, so I'm not even going to bother trying to do another piece of synthetic. But if I do solve for it, I get x is equal to plus or minus square root of -9. But now that we're in the world of complex, and that's fair game, we can rewrite that as our zeros of x equals 1, -1, and then the last two zeros, because it is quartic, are going to be plus and minus. Well, square root of 9 is 3, and it's got that negative, so plus or minus 3i. So if at any point you get down to something quadratic and you can already tell by looking at this that nothing of the rational is going to work, then you can feel free to dive right into typically solving it, giving us our 4 zeros. And now we'll go on to the very last problem. We got a slight little trick to kind of help us approach it. With this very last problem, number 16, we finally see an issue with the rational root test, which is, well, I know my Q, right? It's 1, but the P, the thing that goes on top for those ratios, is always your constant term, and we don't have one. So technically, for that, or us right now, P is 0, and then the other one's 1, so our only option for rational is 0, which doesn't really help us much. However, there is something else there that we can do. What do all of these have in common since we don't have a constant term? They all have an x. So I'm going to rewrite this and pull an x out of everything. So by doing so, I have kind of already two zeros. I have x equal to 0, because we can do that, right? This is a product. We can set both equal to 0. So I already know I have x equals 0 as one of my possible. And then whatever zeros this gives me will be whatever's left over. Well, now I can kind of approach just this smaller polynomial as a new problem. So I'm going to look at the possible roots of just this smaller piece without that x. Well, it's looking at the factors of 24 over 1. So we have plus or minus 1, 2, 3, 4, 6, 8. We have 12 and 24. Whole bunch of possibilities, right? And these possibilities are coming from the fact that if there is no constant term, we're kind of already promised one of our zeros will go right through the origin at x equals 0, because we can factor that x off. Well, now no different than the ones before. I got some possible zeros. I have not the original, although it works there too, but I'm just going to work with the smaller one just for simplicity case of trying these possible zeros and seeing which ones hit. So bring up the calculator, type in your new function, bring up the table to test some points, and I'm just going to start running through it. 1, we get -36. -1, we get 10. 2, I get -40. -2, though. -2, I get a 0. So I'm going to add that to my list. I know that -2 is a 0. And now when I'm doing synthetic, I only have to deal with this smaller polynomial. It does work in the original, But if we already have something more simplified, more factored, we might as well work from there to get it as close to quadratic as possible. So we get 1, 1, negative 14, negative 24. I know I should get a 0 as a remainder. That's the nice thing about doing this synthetic and knowing these zeros. Bring down the 1, negative 2, negative 1, 2, negative 12, positive 24, and bam. That gets a 0. We like it. Now, instead of going from quartic to cubic, we use that smaller bit. We're cubic now to quadratic. And when it gets to quadratic, I always like to write it out just to see if it's nice and easy to factor. And yeah, that's not too bad, right? We have leading coefficient of 1, factors of 12, really negative 12, to give us a negative 1. Well, we need a negative 4 and a positive 3. That'll get us the negative 12, but the middle term of negative 1. And then we set both of those equal to 0. So we get x is negative 3, and we get x is 4. Leaving us over here for our total list of, I'll kind of freshen it up maybe on this side, we get x is 0. We get that from the x we factored out. We get x is negative 2. We got that from testing the possibilities. And then we got down to something quadratic we could factor, giving us negative 3 and 4 as our remaining 2 zeros. So now if I wanted to, given any polynomial, I can look at end behavior of it. I can find the specific zeros of it, given nothing else. I can know the multiplicities, where it'll cross, where it'll bounce, and then test the middle points to get a very accurate graph of each polynomial strictly by hand. So that wraps up 2.5. Pretty important section. 2.6, we move on to rational functions.